So, as I've said before, we are taking regular languages slowly, step by step, because regular languages represent kind of the simplest kind of languages that we're going to be using. And once we do all these different things with regular languages, we will see how we can do the same things with more complicated languages, and we'll work our way up very quickly, really, once we finish doing regular languages, to talking about pretty much anything you can program on a computer. But right now, we are going to talk about regular grammars. And in fact, actually not right now. Right now, we're just going to talk about grammars. Once we've talked about grammars, which is something the textbook assumes you already know about, then we can move on to regular grammars. Now, I'm not assuming that you learned about grammars in discrete structures. So this set of slides teaches you about grammars in general, and then we will move on from this set of slides onto regular grammars. So first we're going to talk about grammars in general in this lecture, and that's a little bit more, there's less restrictions on them in the things we're going to learn about now, and then we'll talk about the special subcase, which are regular grammars. So everybody's familiar with English grammar, and if you have a sentence like "the big dog chased the cat," then we can split that sentence into subject and predicate, and we can split the subject into an article, an adjective, and a noun, and so on. And there are very specific rules for English grammar. Of course, English grammar is much more complicated than the grammar of many languages, but we could say that in order to create this sentence here, what we had to do is we had to say, well, a sentence is made up of a subject followed by a predicate. And what's a subject? Well, a subject is built out of an article followed by an adjective followed by a noun, and so on, right? So we can talk about the rules of English grammar, or at least the rules for constructing sentences like this. Now, sometimes even linguists who are studying English will draw a parse tree for this kind of sentence. And so in the same way that before we said a sentence is made up of a subject and a predicate, we just draw that out using a tree structure, right? So our sentence is composed of a subject and a predicate. Our subject consists of an article, an adjective, and a noun. And eventually we get to kind of the leaves of our tree, which are the actual words that we're using. So if you look at this, all of the leaves on the tree are words in the English language, and the internal nodes on the tree are parts of speech, okay? Or grammatical predicate isn't a part of speech, is it? My English grammar is not fantastic. So grammarian terms, we'll call it, or something. But the important thing to note here is you start with your sentence, you break down into the different parts, and all of the internal nodes in the tree are kind of in one class of things, and the terminal nodes of the tree, right, the leaves of the tree, are all actual words in the English language. So now let's talk about the grammar for an arbitrary language, keeping in mind that now by use of the word language, I mean a set of strings, right? If I say to you, at least for the rest of this semester, what's a language, you should just instantly blurt out at this point, it's a set of strings, okay? So if we have L as a language over an alphabet A, then we can talk about a grammar for L, which is a bunch of grammar rules, right? And they all take this form. And the form is one thing, arrows, another thing, okay? So in this case, we've got gamma arrowing delta, right? So, and we say gamma and delta in this case are strings of symbols, and these symbols are in my alphabet A, and also from my grammar symbols, which are disjoint from A. So this is the formal definition of a language. Let me show you what I mean. I think when you see this example, it'll make sense to you. So let's let A be the alphabet consisting of the symbols A, B, and C. And we're going to say S is our start symbol. So here's a grammar for A star, keeping in mind that A star, remember, is the set of all strings over this alphabet, right? So anything we can come up with. So when you start, you either end up with lambda, or you end up with A followed by something made up of S, B followed by something made up of S, C followed by something made up of S. Let's look at let's try and derive the string CCAB, right? And then you'll see what's going on here. So what I can do is I can say, well, if I start with S, you always start with your start symbol. From S, using this last rule here, I can derive, and we're going to use this double arrow, CS, right? So effectively, I took this single S and expanded it using one of the rules into CS, right? And now from that one, I'm going to expand that into CCS, because again, what I did is I took this single S and I turned this single S into CS using this last rule. Okay. I think what I'm going to do is shrink this a little bit so I have a little bit more room. Let's get that up there, and we'll take this, move it over here. Okay. And so remember, I'm trying to derive CCAB. So now I think you know where we're going here. I'm going to do CCAS because, of course, what did I do? I took this S and I expanded it into an AS using this second rule here, right? And still I don't have enough room, so bear with me. I'm going to do a symbol that is not really part of grammar symbols, but you'll get it. All right, so we'll arrow up to there, and we'll expand that last S into a BS, like so. CCABS, because this S is going to expand into BS. Notice, by the way, the stuff I'm writing in red here is not part of my derivation. I'm just trying to show you what kind of gets expanded. And we're not quite done yet because we still have this capital letter S in here. And the things on the left-hand side of this grammar, which in this case are all just S's, we call non-terminals. They're like the internal nodes on our tree. They're not part of our alphabet, so we can't stop there. So what I'm going to do is I am going to say, well, that one goes to CCAB lambda, because of course we can take S and turn it into lambda using this rule up here. And so now if you look, I've derived CCAB lambda, but CCAB lambda is exactly the same as CCAB, right? And so I have derived CCAB using these rules. Here's a cleaner version of what we just did together as a group, and you'll notice that in here I tell you that this arrow means derives in exactly one step. So this these lines like you know, S goes to BS, that's called a grammar rule or a production rule. And when we're talking about in here, if we have gamma arrows delta, we can say gamma produces delta, or replace gamma by delta, or gamma rewrites delta, or gamma reduces to delta. And in fact, you've heard me already informally, it's not so accepted, but I'll say something like gamma goes to delta, or gamma, I often say expands to delta, even though reduces to is the more polite way to say it, the more official way to say it. So in here, I would say S produces BS, or S reduces to BS, or one of these. And so just like a DFA or an NFA always has to have a start node, every grammar has to have a special grammar symbol called the start symbol. And you have to have at least one production rule. This is one production rule, but there must be at least one production rule that only has a start symbol on the left-hand side. You can have just one, or you can have more than one. And as we've seen in our grammars before, we had the start symbol on the left-hand side in several production rules. And you know, you've probably figured out that you can have a parse tree for these kinds of derivations too, right? So if we say we start with S, we get this S up here, that reduces to AS, right? And so you can see we have the parse tree for our AS, and then and that's just kind of showing you that this piece S goes to the AS, and then this piece S here, right? So that S on the right here actually reduces to BS, and so on. Okay, here's the formal rules, the formal definition of a grammar. Some of this will make more sense as you see more grammars. But a grammar is going to have a finite set of grammar symbols that are called non-terminals. These non-terminals are basically the things that are not in the alphabet, right? And they are also on the left-hand side. I'm writing LHS for left-hand side of my rules. Okay, that's the non-terminals. They may appear on the right-hand side too, right? But definitely on the left-hand side. We also have a finite set of symbols called terminals. These are going to be the letters in our alphabet that we're using in our language. And our non-terminals and terminals have nothing in common. One of our non-terminals will be called the start symbol. It doesn't always have to be the letter S, though we will often use the letter S. And then we need a set of production rules. Notice that we say finite. You can't have an infinite set of production rules. And they take the form that we've seen, where it's gamma arrow delta. And effectively, what this stuff down here is saying is, look, gamma, the thing on the left, can't be empty. You've got to have at least one rule that has S by itself on the left-hand side. And all of the non-terminals have to be on the left-hand side of some production. So the non-terminals have to be on the left-hand side. They have to be expandable. Again, let's look at some more specific examples. It'll probably clear this up, and you can come back and look at this slide again in a couple minutes. Just one point of clarification. We have always said that lambda can never be part of an alphabet. Okay, and we are going to continue to say that lambda is the empty string. It's a special character. You are not going to find it in any alphabet. But just to be clear, in order for us to be consistent with the book, we're going to say that if lambda is a part of a grammar, then it's one of the symbols in the set of terminals. Okay, so generally our terminals are just letters of the alphabet, but it may also, our terminals may also include lambda. All right, so just this final line will continue to say that lambda is not a part of our alphabet from which we take symbols for our strings in our languages, but lambda can be one of the symbols in our set of terminals. Now, it is possible for a grammar to have more than one non-terminal on the left-hand side, and there's nothing about our rules for grammars that say that you can't have terminals on the left-hand side as well. But for the purposes of this class and for everything that we're going to be doing, we are only going to have a single non-terminal on the left-hand side. So that's kind of note 1. And note 2 is, you know, computer scientists like shortcuts, and mathematicians like shortcuts too. And so what we're going to do is if we have a bunch of rules that have the same non-terminal on the left side, so for example, excuse me, all of these rules have the non-terminal s on the left-hand side, right? We can combine these rules by just saying s goes to lambda or as or bs or cs, right? And here we go again. We're using this bar symbol to represent yet another thing, right? We've used bar symbol in our sets to say x such that x is less than 5. We've used the bar symbol to talk about the size of a set, right? We've used the bar symbol for a bunch of things. And now we are also using it as our divider for these rules. And sorry, you just need to be able to kind of tell the difference from context. Just like we have a formal way to represent a DFA as a 5-tuple and a formal way to represent a NFA as a 5-tuple, guess what? We can represent a grammar as not a 5-tuple, but a 4-tuple. Okay? We have a list of the non-terminals, a list of the terminals, we specify the start symbol, and we give all the production rules. Most of the time, we're just going to write the production rules. We're not going to actually use this formal representation. But again, it's something you should be able to do if I asked you to do it, right? Just because one of the things about this class that we're trying to make sure you learn is how to be very clear and very precise and very formal in your language, using language as a as it's normally used, right? So we want you to be skilled with being precise when you try to be, right? We want you to be able to intend to be precise and be precise. So just as an example, if my production rules are the ones we've used so far, right? So remember, this thing actually expands. This is 4 different rules. S goes to lambda, S goes to AS, S goes to BS, and S goes to CS, and we just had it written out on a single line like this to save space. Then our grammar would say our non-terminals are a set, because you could have more than one non-terminals. Right now we only have one, it's S. Our terminals are the letters of the alphabet plus lambda. Notice it doesn't say this is our alphabet, these are our terminal symbols. The start symbol, the one that we're going to start with, is S, and our production rules are P, which is specified by this, or by this. Right? We could say P, like that. So let's come up with a 4-tuple for this grammar. Remember that our 4-tuple consists of the set of non-terminals, right? The set of terminals, the start symbol, and the production rules. So for my production rules, I'm just going to write P is this thing right here. And let's do the 4-tuples. So my non-terminals are the set of all symbols that appear on the left-hand side. So that would be S, A, and B. My terminals are the letters of the alphabet and also lambda, if it exists in here, that could possibly be derived from my non-terminals. So in this case, I have A, I have B, and I have lambda. My start symbol is going to be S, and my production rules, I'll just write P because I defined P up here, right? And we can see that we could get strings like ABB out of this, right? Because we could say something like S goes to AB, which goes to AAB, right? Because I'm going to take that S, expand it into AB, take that A, turn it into AA, right? So that could go to a lambda b, right? Expanding the a into a lambda, which goes to a lambda bb, which goes to a lambda b. Oops, that's supposed to be a lambda, not an a. A lambda b lambda, which is just the string ab, right? So if you look at this grammar, you can see that it produces all strings that start with A's and then end with B's, 0 more A's followed by 0 more B's. So this grammar is actually a grammar for the regular language, A star, B star. A couple more fancy words or phrases that you should know for parties if you want to talk about grammars and sound professional. We talk about a sentential form, which is just a string made up of terminals and non-terminals. So, you know, on the previous page we had a string that looked like this. What was it? It was a lambda capital B, right? And that has some terminals in it and some non-terminals. So, you know, that's a sentential form, and you know, a lambda little b lambda is also sentential form, but you don't have to have non-terminals or terminals for that matter in your string to make it a sentential form. And then finally, you'll see on the previous pages, I've been using this double arrow notation to represent these derivations, and that just says here's how you do one step. If it is the case that gamma produces this delta, then we can take the gamma in here, replace it with the delta, and call that a derivation. More just detailed notation. The double arrow by itself means derives in one step, exactly one step. If you stick a plus on it, that means derives in one or more steps. And if you stick a star on it, that means derives in 0 or more steps. This shouldn't be too surprising. So just to make sure you're clear on this, let's do these questions from the bottom up. So can you get in exactly one step from S to AAB? And the answer is, of course, no. Can we get from S to AAB in more than one step? Well, sure we can, because I think we did it before, but let's just do it real quick. S goes in one step to AB. We can replace that capital A with a little a, big A. And we can replace that next capital A with another little a, big A. So that'll take us to, oops, sorry, little a, and then we replace the capital A with a little a, big A, and there's our B. While we'll replace the capital A with a lambda, so that goes to AA lambda B, which goes to a lambda little b, big B, goes to a lambda little b lambda. Oops, that's supposed to be a lambda, right? And that is the same as little a b. So we can definitely derive little a b from S. We can do it in one or more steps, and we can actually do it in 0 or more steps. It happens to be more, but 0 or more is more. Okay. Now, I showed you one way to derive AAB, but there are, in fact, other ways you can derive AAB. So, for example, here are two different derivations for AAB. And you can see that they both start out the same, right? We start out with the same first step. But then we, in this first one, we're kind of doing what I did in my example and expanding the A first. And in the second one, we happen to be expanding the B first. As of right now, nothing wrong with doing it either way. It's important to note that there's not necessarily a single derivation for a given string. What we will say, however, is that you can have a derivation that you call a leftmost derivation. And when you're talking about a leftmost derivation, that's a derivation where you always replace the leftmost non-terminal first. So that's what I was doing when I was saying let's replace the capital A first, because the capital A was the leftmost non-terminal in our terminal list, right? But strictly speaking, formally a leftmost derivation is a derivation that at each step the leftmost non-terminal of the sentential form is reduced by some production. And of course, we can also say, there's another term which is called the rightmost derivation, and you won't be shocked to hear that a rightmost derivation is the same thing in which we reduce the rightmost non-terminal first. So of course, we've talked about the language, remember a language set of strings, right? The language represented by a regular expression. So for example, we've talked about the language of A star is this set, right? Because there's our set of strings. We can also, of course, talk about the language represented by a grammar. So if we have this particular set of production rules, right? That also produces the same language, right? That's also the language of all strings that are made up of 0 or more A's. And formally, what is the language of a grammar? Well, the language of a grammar is just, right, so here's our language of a grammar, is just the set of all strings X such that X is in capital T star. What was T? T was our terminal. So this just says X is a string of terminals, and it's possible to get from our start symbol to X in one or more steps, right? So it just says the language of a grammar is all the strings that that grammar can produce. It's exactly what you would think the definition of the language of a grammar would be. Now, finding a grammar for a finite language can be really simple, right? So a grammar for this particular language here could be as simple as S goes to A, and S goes to B, and S goes to C, and S goes to A, B, C, right? So there's a grammar for L. I haven't expressed it as a for tuple, of course. I've only given you the production rules. I gave you the production rules in the long form. Another way to write this in shorthand would be S goes to A, or B, or C, or A, B, C. But I hope that you see that if you have a finite language, it's trivial to write a grammar for it, right? Even if it's a finite language with 100 different strings in the language, you could just have 100 of these production rules if you wanted to. Of course, it's trickier when you get to an infinite language. There's a theorem that says if a language is infinite, then some production or sequence of productions must be used repeatedly to construct the derivations, right? What does that mean? If your language is infinite, there has to be some loop in your production rules, right? And so, and that loop might be a direct route where S single arrow goes to AS, right? Or it could be something a little bit more complicated, like S goes to AB and B goes to BBS, right? So you have to keep, they're interdependent. You probably heard about the pigeonhole principle in discrete math. And the pigeonhole principle, just as kind of some background, the pigeonhole principle, the short story for the pigeonhole principle is if you have 10 pigeons and 9 holes, some hole has to have at least 2 pigeons, right? If you look at our picture here, there are actually 2 pigeons. I found this on the web. I didn't cite where I found it, which is pretty bad, sorry. but it's a cute picture. But pigeonholes really, if you go to the UK, for example, instead of saying, put something in my mailbox, in the computer science department, they'll say, put it in my pigeonhole. And these kinds of mailboxes that you find in most academic departments where you can throw papers into individuals, what we would call in the States a mailbox. In the UK, they call them a pigeonhole. So doesn't matter which. The whole idea of the pigeonhole principle is if you have, say, 27 pigeonholes, but you have 28 pieces of paper, there's going to be at least one pigeonhole that has 2 pieces of paper in it, right? If you have 9 holes, 10 pigeons, somebody's going to get 2 pigeons. And that's really, as long as you keep that in the back of your head whenever you're thinking about pigeonhole principle, it's easy. So let me give you a high-level overview of this theorem, right? So if a language is infinite, then some production or sequence of productions must be used repeatedly to construct the derivations, okay? So here is a somewhat loose but reasonable version of this proof. I'm not going to ask you to do proofs like this, but just to give you a feel, okay? If we assume the language is infinite, then there's no bound on the length of strings in the language. Strings can be as long as we want, right? Arbitrarily long. But that means if a string can be arbitrarily long, then there cannot be a bound on the number of derivation steps that we need to take in order to derive that string, right? But we said that we have a finite number of production rules. That was way back a few slides ago where we said, you know, a grammar has a finite number of production rules. Let's call however many production rules we have n. If you pick a derivation that uses n plus 1 steps, right, then by the pigeonhole principle, we're using n plus 1 steps, but we only have n production rules. We must use some rule at least twice. QED. Okay, so here's a problem from the textbook. It says, given the following grammar, looks like we have 2 non-terminals here. We have an S and D. And our terminals look like they come from the digits 0 through 9. Find a rightmost derivation of the string 7801. So they're asking us for rightmost derivation. Let's shrink this a little bit so we have some room. Something I guess I didn't say before, but generally we will use the symbol S if it's a non-terminal to refer to the start symbol. But the other thing that we tend to do is we put whatever the start symbol is for our grammar, we make sure that the first rule that we list in our production rules starts with whatever our start symbol is. But we're gonna try pretty hard to keep S as our start symbol a lot of the time. But if we do have S as our start symbol, not only will there be an S as a non-terminal, but you'll also see that the first production rule will have S in it. Okay? All right, so let's just shrink this down. Put it up there. There we go. And let's do this. So we want to have a rightmost derivation of the string 7801. Okay? And it looks like that we need to, if you just kind of inspect this grammar, right? If you use your wits and look at this grammar, right? What are our choices for S? S can go to a single digit, right? This is kind of the last step, whatever we do. Or it can go to a digit followed by S, right? And since we want 4 digits in our number, it looks like we need to do something like S. Our first step is going to be S goes to DS. And now, because we're trying to do a rightmost derivation, we need to expand the rightmost non-terminal first. So that means that we're going to have it go to D followed by DS. And we'll repeat this a couple more times. We'll take those DDs and we'll expand that S to a DS, right? So again, I'm expanding this S, the rightmost non-terminal, into DS. And we'll expand that into D, D, D. And this last time, I'm going to turn this S just into a D, right? And then again, we're doing a rightmost derivation, so now we need to expand this D here on the right. So that's going to go to D, D, D1. And now we'll expand the rightmost D again. So that'll go to D, D, O1. And sorry, non-traditional notation, but I'm running out of space. That will go to D801, which goes to 7801, and we're done. Okay, here's a problem from the book that is equally easy. It's just a little bit painful. So we have this grammar, right, which is a grammar of braces, it looks like, right? Square braces, square brackets, you might want to call them, right? And S can either go to a lambda or S followed by square brackets with an S inside. And it says, for each of the following strings, construct a leftmost derivation, a rightmost derivation, and a parse tree. Okay, so let's do this first one first. Let me shrink that up there a little bit. So I want to do, let's do a leftmost derivation for this. All right, so leftmost derivation. Well, we've got S. Don't have much choice for the first step, right? That goes like that. And then the first thing we need to do is expand the leftmost non-terminal, which is this guy. And since we have nested square brackets here, that guy is just going to go to lambda, right? And now we expand the leftmost non-terminal, which is the S in there, so that will go to, let's see, we have lambda bracket, and then we're going to have S bracket S, like that, right? Because what we've done is we've taken that S in there and expanded it into that piece. That looks right. Okay, and now we're doing a leftmost derivation, and I think if I just replace everything with lambda, we're good. I just need to make sure I do it in the right order since we're doing a leftmost derivation. So that goes to lambda bracket, we'll replace that S with a lambda, bracket S, bracket, bracket, which goes to lambda bracket, lambda bracket, lambda, bracket, bracket. So there's our leftmost derivation. I'm going to leave the rightmost derivation of this one to you, but let's do a parse tree for this. So let's see if I can shrink this up a little bit, or maybe just move it up. Hang on. All right, we're going to lose the thing at the top, I think, but there we go. Let's put that. Let's see, maybe if I shrink it a wee bit. There we go. That's not bad. Okay, so let's just do a parse tree for this derivation we just did. And our parse tree, we get the S at the top, right? And what I'm going to do for this parse tree is I'm just going to step through each step here. So kind of got, oops, I've got that one done. Now let's do this one. So the S goes to S bracket S bracket. And you'll see just like with our English language parse tree that we did at the very beginning, the terminals end up as leaves on the tree and we have to expand the non-terminals. So the next thing that we expanded in here was the S inside the bracket, right? And we were doing a leftmost derivation, so next we expanded this leftmost S into the lambda, and then we expanded this S into the S bracket S bracket, right? So we are up here now. If you just look at the leaves of the tree so far, that shows us what's in our sentential form, right? Again, we are going to expand the leftmost non-terminal. We're here. We expanded this one. We're expanding this one. So that goes to lambda. And then we do the next one, and that goes to lambda. So there you go. That is the leftmost derivation and the parse tree for that. Now what I'm going to do is why don't we just do the rightmost derivation for the second one, because it's pretty messy, and then I'll leave it to you to do the leftmost derivation for that and the parse tree for that. So let me clean up my screen. Hang on. And now we are going to try and do a rightmost derivation for it. It's open, open, close, open, open, close, close, close. Let's just see, did I get that right? Hang on. That's two opens and a close, so these guys are together, and we have these outer ones match up. And then we have a pair of nested ones there. Yep, that looks good. Okay, let's try a rightmost derivation for this. Right? We don't have any choice for our first step. We start with S goes to S bracket, S bracket. And then if we just kind of look at this, we can't put any more outer brackets in there, right? So these two brackets here represent these two brackets here. And this guy's going to go to a lambda eventually, except that we are doing a rightmost derivation. So maybe what I'm going to do, I'm just going to color code these a little bit. And I'm going to put a little red dot there, a little red dot there, and I'll put a little red dot there and a little red dot there just to remind me what we're doing. So we have to do a rightmost expansion anyway. So, and we do want some more brackets inside, so let's see what we get. So we say we're going to go to S, and that guy, like I said, that first S is going to go to a lambda, but not yet. And S bracket, bracket, oops, with an S inside, right? So these two are still that red one, and now it gets interesting, right? Because, let me get another color. This S here is going to represent this piece, and these two, I think, are going to represent this piece, right? And now let's keep going. We have to do rightmost derivation, and we need another pair of brackets in here, right in here, so this needs to get expanded once more. So that goes to S bracket, S bracket. Now I'm going to expand this S into S bracket, S bracket. And then we put the final two closed brackets on. So just to color code it for our own use, right? The color code is not part of this. Those are the red outer brackets. And then inside we have the green brackets, and now we'll add a couple more brackets. We'll make these ones purple. All right. And these purple ones correspond to that. But we still have not done this piece here, right? But of course we need to go from right to left. So let's just look for a minute. We have bracket, bracket, wait, so we have the triple kind of bracket thing, right? And then we have the two out. So this one's going away, right? And then this one needs to expand to another set of brackets. So we can't expand this one to another set of brackets yet, but eventually, let's say, that's going to be the orange brackets, and let's make that orange instead of green. Okay. So again, we're doing a rightmost derivation. So we need to expand this S, So we will expand that one just into a lambda now, because that's kind of done. So that's going to go to, actually let's go to the next line. Start writing smaller. It's going to go to S bracket, S bracket, S bracket, lambda, bracket, bracket, bracket. Great. And now we need to expand, do rightmost expansion again. This one corresponds to that one, which is just another lambda. So that goes to bracket S bracket, lambda, 1, 2, 3. All right. Now we are up to what I think is our orange one, right? So that needs to expand again into another set of brackets before we get rid of it. So we have bracket, and we're going to expand that orange into S bracket, S bracket. And then we copy everything else that we have, bracket, lambda, bracket, lambda, 1, 2, 3. I am completely running out of space. Hang on, let me see if I can shrink this slightly. I think as I shrink this, I'm going to end up messing up some of these lines up at the top, but bear with me. Let's see what happens. Yeah. So ignore the lines way up at the top. Okay. And let's see. So, and I'll try and write more small. So we're doing rightmost derivation. So now we need to reduce that one. Well, so we will do bracket S, bracket, lambda, bracket, and then we've got the bracket, lambda, 1, 2, 3. And rightmost derivation, we only have one non-terminal left. So we go to bracket, lambda, bracket, lambda, bracket, bracket, lambda, bracket, lambda, 1, 2, 3. And I'm really hoping that when I get rid of the lambdas, I have, I'll just write an equal sign there, right? 1, 2, 1, 1, 2, 1, 2, 3. Hurrah, I think we did it. And again, you could do a parse tree for this, right? It would start out by saying, let's just look at the first couple steps. We had our S, and that went to S bracket, and then we would expand this one and so on. This one, right? I'm not going to do that parse tree. You can do that as an exercise. Of course, we said that if you have an infinite language, you have to have a some sort of way to derive the longer strings. That comes from recursive productions. We say a production is recursive if the left side appears on its right side. So, for example, here we have S goes to AS. We can also say it's indirectly recursive if there's a couple of steps that get us back to where we were. So here we have S goes to little a, but big A goes to BS. So eventually we get back to that S. Whoops, and I think I gave away my answer to this question here. A grammar is recursive if it contains at least one production that is recursive or indirectly recursive productions. So are all grammars for infinite languages recursive? Yes, of course they are. So now we just need to talk about how do you build a grammar, right? And so, you know, how do you use your wits to make a grammar? And it's just to kind of, you know, how do you think about building these things up? So let's just talk about this and let's do a few examples. So this first example, and I'm just going to give you the production rules. I'm not going to give you the 4 tuples. So let's look at this first one. We need to find a grammar for the language a to the n such that n is an element of n, right? That's the same as saying we're finding a grammar for a star, which we've done before. It's you've probably remember how to do this one, but we're just going to say, well, you're going to start, and either you're going to go to an a followed by the start symbol again, or you'll go to lambda. Yeah, it's pretty easy, right? Because we just keep kind of building up the a's. This next one a to the n, b to the n, right? So 0 or more a's and b's, right? So 3 a's, then 3 b's, or 27 a's and 27 b's, or lambda, the empty string, right? And in fact, no, this is not a regular grammar. But just because it's not a regular grammar, remember, we're not doing regular languages right now. We're just doing, we're not doing regular grammars right now. We're just doing grammars. And so, so we can do a grammar for this. It will not be a regular grammar because our language is not a regular language. But that's okay. So when you're doing something like this, a to the n, b to the n, you need to kind of think about how you build it up. The important thing is every time you add a as a non-terminal, you have to add b as a non-terminal. And what we can't do is we can't do something like this. We can't say S goes to ABS as a production rule, because then we could get something like S goes to ABS, goes to ABS, which would mix up the order of our A's and B's, right? And here it's all the A's come first, then all the B's, right? A to the n, B to the n. So that's no good, right? So we can't do that. So let's get rid of that and try again. Okay. So what we're going to do is we need to have the same number of A's and B's, but we need them to kind of bubble out from the middle, right? So our rule is going to look something like this. We're going to say S goes to ASB, right? So every time we put that S in, the A's are on the left and the B's are on the right, or lambda. And if you look at that, then if I'm trying to derive a string like AABB, you'll see what we get is we get something like S goes to ASB, goes to AASBB, goes to AA lambda BB. And we got it. So that's pretty good. Okay. Finally, let's do this last one. Now we want AB to the n, right? The language AB to the n, and that is in fact a regular language, right? So it's just a bunch of ABs, 0 or more ABs. And that was in fact what I wrote in red before, right? So we're going to say S goes to ABS or lambda, right? So every time we put in our letters, we'll put in our ABs, and then we could expand some more if we wanted. I don't expect that finding these 3 languages for this first slide would be easy for you. It does take a little bit of practice to understand how these things work. I think what you need to kind of really look at and really note here is the difference between how these 3 grammars work, right? So this first one is just a single letter building it up. It's pretty easy, and in fact, you know, you might want to note that we could also have said this S goes to SA or lambda, right? Nothing wrong with that. And similarly for this last one, we could have said S goes to SAB or lambda. That would have been fine. But this middle one, where we really need to kind of build it up from the middle, it's almost like I keep thinking of it bubbling out of the middle. It's really important that we get that S in the middle. We're expanding from the middle. So it takes a little bit of practice. So these are some problems from the book that do not have the answers. There's even more problems from the book that give you the answers. Of course, remember that the book does not give you, the answers that the book gives you are not the only answers. Lots of these can be done in lots of different ways. Why don't we just try and do a couple of these, right? So I'm not going to do them all, but we'll do a few just so you get some practice with this. Why don't we do this first one, this second one. Definitely want to do the odd palindromes. I want you to see that one. And I don't know, maybe we'll do this one. Okay. So let's see, this first one, let me move this up a bit. Okay. The first one looks like it's strings that have, it always has an A in it, and then it has 0 or more B's in front of it, right? So this is actually represented by the regular expression B star A. So what I think I'm going to do, when you look at these things, you want to kind of say what gets built up and what's left over at the end. Up till now, left over at the end has been lambda, right? But it's not always the case. So for this grammar, I think we might actually be able to squish it onto one line. Let's see if I can do that. I'm going to say S is going to go to either BS or A, right? So I build up as many B's as I want, and the last thing I do is replace that S with an A. All right? This next one, why don't we underline it in green? We'll do this one in green. B, A to the N, B. So it starts and ends with a B, and then it's got 0 or more A's in the middle, right? So another way to write this, if we were just writing it as a regular expression, would be B, A star B, right? So what I'm going to do here is I'm going to get rid of the part that that we don't, that kind of stays the same early on. I'm going to say S goes to B, A, B. And then A is going to go to AA or lambda. And that way we get the B at the front and the end right away. And then we stuff in as many A's into the middle as we want. Okay. This third one here I'm not going to do, but I'm going to say, look, it's exactly the same as our A to the N, B to the N one, except in the middle we're not going to stuff a lambda, we're going to stuff a B. So it's the same as the previous example we did, where you're bubbling out A's and C's, but in addition to S going to, come on, we'll do it real quick. So I'll do this one in purple, let's say, if I can get purple up. So this is going to be something like this. S goes to ASB, or, oops, sorry, S goes to ASC, or stick a B in the middle. All right. Let's do this next one here. A to the 2N, N is an N. So it's we have to always add pairs of A's. So we can have 0 A's, 2 A's, 4 A's, and so on. So this is actually the regular expression AA star, right? And again, relatively straightforward. There's no bubbling here. It's bubbling from either side. S can go to 2 A's and an S, or lambda. Again, I'm doing these pretty quickly. I don't expect that you can do these this quickly yet. I just expect that if you kind of follow along with me, you will, and then do a bunch of these, and also just go and do these on your own, make up your own problems. You'll be good. Okay, so the only one here that remains that I want to do is this odd palindromes one. And you need to know what a palindrome is, and a palindrome is, of course, a string that the beginning and end repeat. So here's some odd palindromes. I'll do them in purple over ABC. So you have to have A's at the beginning, B at the beginning and end, another B maybe, and then we'll put an A in the middle, right? So it reads the same way if you read it forward or you read it backwards. Or C, 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 C is also an odd palindrome, right? And the odd just refers to the number of letters, right? So whether you read it this way or this way, it's the same. And this is another case of bubbling out, right? Whenever you put a C at the beginning, you have to kind of put a C at the end. So for this one, I'm going to say something like, we're going to start by bubbling out the letters. So we could bubble out an A on either side, or we could bubble out a B on either side, or we could bubble out a C on either side, right? And I can't actually fit, I would do some more ors here, but I can't fit on this line, so I'm just going to start another line, but this is the same kind of thing. And once we've done a bunch of bubbling, we can put in the middle an A or a B or a C. So what I want you to try and do is take these two palindromes and make up a few more and confirm that what I've written here actually works. And if you derive a few of these, I think you'll see how this works, and it'll give you a better feel for this bubbling out that I'm talking about. And I encourage you to do these too and do some other problems from the book. I'm sure I've given you a bunch of homework problems. So let's suppose that we want to take the union of two languages. There's a really, really easy way to start this, okay, or to do this. And what we're going to assume for a minute is that we have two different grammars for two different languages, and we want to take the union of those two grammars. We want the union of those two languages. So maybe we have, for example, down here, the language A to the N, B, C to the N, and B to the M, A to the N, right? So these are two different languages. And I have a grammar for this one, and I have a grammar for this one, and I want to figure out the union of those two. And what I say up here is suppose that the start symbol for grammar 1, G1, is S1. So let's do a grammar for this one that starts with S1. So we've got A to the N, B, C to the N. Well, we just did that, didn't we? So we'll just use S1 instead. So S1 goes to A, S1, C, or B. And we need a grammar for the second one, which is B to the M, A to the N. M and N are natural numbers. So this is just actually the language B star, A star, right? This first language here is not regular, but the second one is. So just a bunch of B's followed by a bunch of A's. So maybe we'll have our second grammar be, I'll do that in a different color. So let me underline this piece, and we'll underline this piece in blue, so you know that was the first grammar, and we'll say S2 goes to, let's see, a bunch of B's and then a bunch of A's. So I think what I'm going to do is I'm going to say that what we do is we start with the B's, and we'll do a bunch of B's, or we'll go to, I don't know, capital A, and A will go to little a, big A, or lambda. And I think if you look at this, you'll see that this derives, that you can get all the strings that are in this second language here. A bunch of B's, 0 or more B's, followed by 0 more A's. Okay? All right, so let's just look at what I have here before. Suppose that the start symbol for grammar G1 is S1. Well, let's call this grammar G1, and it starts with S1. Suppose that the start symbol for grammar G2 is S2. Let's say this is S2, right? And sorry, this is G2, and it starts with S2. And G1 and G2 have disjoint sets of non-terminals. That means that all of the non-terminals in this first grammar do not appear in the second one, and vice versa. So the only non-terminals in the first grammar are S1, no S1 down here. The non-terminals in here are S2 and A, and neither of them appear there, so we're good. And if I want the language that represents the union of both of these languages, right, then what I can do is I can say, all right, well, I'm just going to add one more production rule. You ready? I'm going to put it at the very top. I'm going to stuff it actually up here. And I'm going to say S goes to S1 or S2. And if I do that and I take all of these production rules together, that forms the language that is the union of these, right? So start and either go, after you start, you either follow this path to create a language that's in the, a string that's in the first language, or this path to create a string that's in the second language, and the result is you end up with a string that's in the union of these two. Okay, so in this slide, what we're trying to do is we're trying to concatenate two languages, right? So we're trying to have instead of a string the union of two languages, we're saying take one string from the first language and one string from the second. Right? And I'm using the same two languages as examples again, so theoretically I can paste those grammars. So here you go, here's the grammar from the other slide. In blue I have the grammar for this first language, and in purple I have the grammar for the second language, so there's my second language grammar, right? And what I want to do is, instead of having strings that come from either the union, I want to do the concatenation. So I want all my strings to start with A to the n, B, C to the n, and then end with B to the m, A to the n, right? And again, this is pretty easy if I just add one more step here, which is S goes to S1, S2, then you'll see that this whole grammar in here, if it's taken as a whole, represents a grammar for the language that is G1 concatenated with G2. Okay, so one last way to, this is kind of the rules for quickly making grammars from other grammars. In this case, we're going to try and come up with how to do the star of a grammar. And so the question is, if you have a grammar G1 that starts with S1, how do you get a grammar for the closure of that, the star of that grammar? And so as an example here, I said let's find a grammar, we don't need so big, a grammar for AB star. So a grammar for AB, of course, is very easy because that's just a single string. And this says, well, if you start with S1, right? And so if you already have a grammar for the thing that goes inside of the closure, right? For example, here AB that starts with S1, then to turn that into another grammar for the language AB star, all you do is this trick, right? So we're just going to add that rule. We're adding the rule S. Notice I'm putting it above because I want S to be my start symbol. Goes to S1S or lambda. And if you take these two rules together, I think you'll see that we have the rule for AB star. Pretty cool, huh? Okay, so just to wrap up, we've talked so far about grammars. Just kind of generic grammars. This is something that you didn't necessarily learn in discrete structures, but many people will have learned already, so it's in a much earlier chapter in the book than we're mostly working in. But what we're doing is we've talked about grammars in general in this slide set, and in the next set of slides we'll talk about a subset of grammars called regular grammars.